Inside an ordinary-looking factory in the Netherlands sits a machine more strategically important than some aircraft carriers. It costs hundreds of millions of dollars, contains roughly 100,000 parts, and must be moved across the world using cargo planes, trucks, and dozens of containers. China cannot simply order one. Without this machine, mass-producing the smallest and most powerful chips used for artificial intelligence becomes dramatically harder. Washington wants to keep it away from Beijing. Beijing wants to break the dependence. And Europe controls the company caught between them. The machine is called EUV lithography. The company that builds it is ASML. And this may be the most important technology company most Americans have never heard of. Every advanced chip begins as a design. NVIDIA can design an AI accelerator. Apple can design a processor for the iPhone. But those designs are only digital instructions until factories print them onto silicon. That printing process is called lithography. Imagine projecting a blueprint onto a wafer, then repeating the process layer after layer until billions of microscopic transistors form an electronic city. The smaller those features become, the more computing power engineers can place inside the same area. For decades, chipmakers kept shrinking the blueprint by using shorter wavelengths of light and increasingly complex optics. Eventually, ordinary deep ultraviolet lithography reached a wall. Engineers could extend it through immersion, advanced masks, and repeated patterning. But every extra step added time, cost, and opportunities for defects. The industry needed a different kind of light. Extreme ultraviolet light has a wavelength of just 13. 5 nanometers, close to the edge of the X-ray spectrum. It can draw far smaller features than traditional systems. But EUV light creates a brutal engineering problem. Almost everything absorbs it. Normal lenses are useless. Even air gets in the way. So an EUV machine must operate inside a vacuum and guide the light with mirrors polished to extraordinary precision. ASML says that if one of those mirrors were enlarged to the size of Germany, its tallest imperfection would be about 1 millimeter. And generating the light is even stranger. Inside the system, tiny droplets of molten tin fly through a chamber thousands of times every second. A laser hits each droplet, then a second, more powerful pulse turns it into plasma. That plasma emits EUV light. Mirrors collect the light, shape it, bounce it through a mask, and focus the pattern onto a silicon wafer moving at extreme speed. The tolerances are measured in nanometers. A vibration from the floor, a microscopic contaminant, or a tiny temperature change can ruin the exposure. This is why the machine contains around 100,000 parts and depends on a network no single country can reproduce quickly. Zeiss in Germany supplies the optical system. Specialized technology from the United States helps create the light source. Thousands of suppliers contribute sensors, lasers, stages, vacuum systems, software, and materials. ASML integrates all of it. The company did not begin as an obvious monopoly. It began in 1984 as a joint venture between Philips and ASM International, with a small team in the Netherlands. Its early machines struggled to win customers against established American and Japanese competitors. By the late 1980s, ASML had few customers, consumed cash, and could not stand on its own. One shareholder wanted out. Philips was cutting costs. The young company came dangerously close to becoming a forgotten European technology experiment. Then came the PAS 5500. The platform improved productivity and precision, attracted critical customers, and gave ASML enough momentum to become independent. The company went public in 1995 and poured capital back into research. But its most important decision was still ahead. In the 1990s, scientists knew EUV might extend Moore's law. They also knew it might never work. The light source was too weak. Mirrors lost energy at every reflection. Contamination destroyed performance. A machine could demonstrate the physics in a laboratory and still fail completely on a production line. ASML placed a bet that lasted roughly 2 decades. It worked with research laboratories, suppliers, and chipmakers, spending billions while deadlines repeatedly slipped. Intel, Samsung and TSMC helped finance development because they understood the alternative. Without a new lithography system, the economics of shrinking chips would eventually collapse. ASML shipped its first pre-production EUV system in 2010. It was not yet ready to transform the industry. The machine needed more power, greater reliability, and enough speed to process wafers economically. Year after year, engineers improved the source. More light meant more wafers per hour. Better mirrors preserved more of that light. Cleaner chambers reduced interruptions. Software corrected distortions that human operators could never manage manually. Around 2020, EUV finally entered high-volume manufacturing. That moment changed the balance of technological power. TSMC and Samsung used EUV for leading-edge production. Intel adopted it for newer process generations. NVIDIA's most advanced AI processors rely on foundries that depend on ASML's lithography ecosystem. ASML did not manufacture the chips. It manufactured the ability to manufacture them. In 2025, the company reported 32.7 billion euros in sales and 9.6 billion euros in net income. It sold only 48 EUV systems that year. That small number reveals how unusual this business is. Each machine is infrastructure, installed inside a highly controlled fab and supported for years. Now ASML is moving to high-NA EUV. The new platform increases numerical aperture from 0.33 to 0.55, allowing smaller features and supporting production beyond today's leading nodes. The first modules were shipped to Intel at the end of 2023, and the platform is intended to move into high-volume manufacturing during the middle of this decade. But the deeper ASML moves into the future, the more political the machine becomes. China is the world's largest market for many electronic products and has invested enormous sums in its domestic chip industry. Chinese fabs can manufacture a wide range of chips using older technology, and those mature node chips remain essential for cars, appliances, industrial equipment, and military systems. But China has not been allowed to buy ASML's EUV systems. Export licenses for the most advanced equipment have become a central instrument in the technology contest between the United States, the Netherlands, and China. The logic is straightforward. Advanced chips power frontier AI systems, supercomputers, and sophisticated weapons. Restricting the machines used to manufacture those chips can slow a rival more effectively than restricting a single finished processor. Yet the strategy is not a perfect blockade. China can stockpile permitted equipment, improve older deep ultraviolet processes, use multiple patterning, develop domestic tools, and redesign chips around manufacturing constraints. These methods can produce capable technology, but they often demand more steps, lower yield, and higher cost. Export controls, therefore, create a race. The United States and its allies are trying to preserve a moving technological lead. China is trying to make the choke point disappear before the gap becomes permanent. ASML is trying to obey national security rules without losing one of the world's largest semiconductor markets. And the Netherlands faces an uncomfortable reality. A company with roots in a leaky shed now influences the strategic choices of superpowers. There is another vulnerability hidden inside the Western advantage. ASML itself is not independent. Its machines rely on suppliers across Europe, the United States, and Asia. A disruption at a specialist optics factory, laser facility, or precision component supplier could slow the entire chain. The monopoly is real, but it is built on interdependence. That is what makes the EUV story larger than one company. Modern technology is often described as software floating in the cloud. In reality, artificial intelligence rests on factories, electricity, chemicals, mirrors, lasers, and engineers. The most advanced algorithm in the world is useless if nobody can manufacture the chips required to run it. For now, ASML holds the narrowest point in that physical system. China may eventually develop a competitive alternative. New technical approaches may change the economics of lithography. Export rules may tighten, loosen, or push customers toward different supply chains. None of those outcomes is guaranteed. But every year the leading edge advances, the challenge becomes harder. ASML is already shipping machines based on knowledge accumulated across decades, thousands of suppliers, and countless production failures. Money can accelerate research. It cannot instantly purchase experience. So the defining question in the global AI race may not be who builds the smartest model. It may be who controls the machines that turn intelligence into silicon. And what happens when the most important machine in the world becomes something one superpower is not allowed to buy.